Good day everyone, my name is Muhammad A. Abdullah, and for today's video, we're gonna be learning about solving molality, boiling point elevation, and the first law of thermodynamics, which is the calculation of heat, work, and internal energy. Molality is one of the ways to express the concentration of a solution. Molality is equal to the quotient of the moles of solute present in the solution and the mass of solvent in kilogram present in the solution. Here's an example. A 4 gram of sugar cube is dissolved in a 350 milliliter teacup of 80 degrees Celsius water. What is the molality of the sugar? Given that the density of the water at 80 degrees Celsius is equal to 0.975 gram per milliliter. Molality is the number of moles of solute per kilogram of solvent. So first, let's determine the number of moles of sucrose in 4 gram, which is your solvent. In order to get mole, we will use the formula mole is equals to mass over molar mass. So, mole is equals to mass of solute, which is 4 grams, divided by the molar mass of the sucrose. Molar mass can be calculated through adding the atomic weight of the constituent atoms. It is solved as follows. The result of the mole of solute is 0.0117 mole. Moving on, we must determine the mass of solvent in kilogram. We derive the formula of density in order to find the mass of solvent. Density is equals to mass over volume, and from that we can say that mass is equals to density times volume. Mass is equals to 0.975 gram per milliliter times 350 ml, which is the volume. Now the mass is 341.25 gram, and in kilogram is 0.341 kilogram. Now we can proceed in solving the molality of the solution. Molality is equals to mole of solute over mass of solvent, which is equals to 0.0117 mole over 0.341 kilogram, which is equals to 0.34 molal. Therefore, the molality of the sugar solution is 0.034 molal. Next is the boiling point elevation, which is one of the colligative properties of solution. Boiling point elevation describes the phenomenon that the boiling point of a liquid will be higher when another compound is added, meaning that a solution has a higher boiling point than a pure solvent. So, in order to find the boiling point elevation, we need this formula. Delta T sub B is equals to I times K sub B times M. The change in boiling point of the solution containing non-volatile solute is equals to I, which is called the Van Hoff factor. And the K sub B is the molar boiling point elevation, which is constant to a certain solvent and has a unit of degrees Celsius times kilogram over molality. And M denotes molality, which we already know how to solve. For example, calculate the boiling point of a 3.5% solution of sodium chloride in water. We can say that 1 kilogram of the solution contains 0.035 kilogram of sodium chloride and 0.965 kilogram of water. Since the molar mass of NaCl is 58.5, the number of moles of NaCl in 1 kilogram of the solution is 35 gram over 58.5 gram times mole to the power of -1 is equals to 0.598 moles. The molality of NaCl in 1 kilogram of the solution can be calculated as M is equals to 0.598 moles over 0.965 kilogram, which is equal to 0.619 molal. The boiling point elevation constant for water is 0.512 degrees Celsius kilogram over molal. Since in ACl dissociates into two ions, the Van 't Hoff factor for this compound is 2. Therefore, the boiling point elevation delta T sub B can be calculated as follows. Delta T sub B is equals to 2 times 0.52 degrees Celsius per molal times 0.619 molal, which is equals to 0.643 degrees Celsius. Now that we got the boiling point elevation, we can get the boiling point of the solution, which is equals to boiling point of the pure solvent plus the boiling point elevation, which is equals to 100 degrees Celsius, which is the boiling point of the water, plus 0.643 degrees Celsius is equals to 100.643 degrees Celsius. Therefore, the boiling point of the 3.5% in ACl solution is 100.643 degrees Celsius. Now, let's proceed to the first law of thermodynamics, which is about the calculation of work, heat, and change in internal energy. The equation for the change in internal energy is delta U equals to Q plus W, where delta U is the change in internal energy, Q is the heat, and W is the work. The equation for work is W is equals to negative P delta V, where P is equals to pressure and delta V for change in volume. And for heat is Q is equals to C delta T, where C is the heat capacity and delta T is the change in temperature. For example, the heat, work, and internal energy of a gas compressed from 100 ml to 35 ml at a constant temperature against a constant external pressure of 0.98 atm. Given that the change in temperature is 0 Kelvin, initial volume of 100 ml or 0.1 liter, final volume of 35 ml or 0.035 liter, and constant pressure of 0.98 atm. From the given, we can say that the change in volume is equal to negative 0.065 liter. In calculating the work is equals to the negative pressure times change in volume. Work is equals to negative 0.98 atm times negative 0.065 liters. In result, work is 0.637 LATM. But by converting to joules, we get 6.453 joules as the work. For the heat is equals to the heat capacity multiplied to the change of temperature. But in here, the change of temperature is equals to 0. So the heat is 0 joules. For the change in internal energy, delta U, or the change in internal energy, is equals to Q plus W, which is equals to 0 joule plus 6.453 joules and results to 6.453 joules. Therefore, the heat, work, and internal energy of the gas that's compressed are 6.453 joules, 0 joules, 6.453 joules, respectively.